Welcome to a screencast on molecules and molecular compounds. Now, you probably know that when atoms of different elements combine together in specific arrangements, they form what are known as chemical compounds. And we've already dealt with one type of chemical compound called ionic compounds. These are made up of ions, which are atoms that have gained or lost electrons, and then these positively and negatively charged ions attract each other, and that's what holds ionic compounds together. But of course, there's another type of compound called a molecular compound, and molecular compounds consist of atoms that are held together by shared electrons, not by positive-negative attraction. The basic unit of a molecular compound, in fact, this is where it gets its name, is a group of atoms bonded together via shared electrons, and that's called a molecule. And worth noting, these shared electrons, pairs of shared electrons, are called covalent bonds. We'll talk about this later in the course in more detail. And for this reason, molecular compounds are sometimes also called covalent compounds. Now let's look at a couple examples. Let's start with hydrazine, which is a rocket fuel, in fact. Hydrazine has the formula N2H4, and it consists of 2 nitrogen atoms and 4 hydrogen atoms, and they are bonded together in exactly this way. Nitrogen is bonded to nitrogen in the sort of center of the atom, and then each nitrogen has bonds to 2 separate hydrogens. So those are a couple representations of a molecule of hydrazine. Here is another one. This is called a ball and stick model. And the blue spheres here represent nitrogen atoms, and the sort of grayish ones represent hydrogen atoms. And these are just different ways of representing hydrazine. Notice, of course, that the two on the right actually show what atoms connect to which. And the one in the middle, what's called structural formula, actually gives a symbol for each element. The one on the right sometimes shows the geometry a little bit more. A somewhat more complicated example is caffeine. It has the formula C8H10N4O2, and a caffeine molecule consists of 8 carbon atoms, 10 hydrogen atoms, 4 nitrogen atoms, and 2 oxygen atoms bonded together in exactly the way that's shown here. Notice that each line represents a covalent bond between 2 atoms, and 2 lines represent what's called a double bond. And we'll talk about bonding in more detail down the road. Here is the ball and stick model for caffeine. And this is what's called space-filling model. And this space-filling model shows the actual structure of the molecule a little better, in the sense of it shows all the space that it occupies. But it's sometimes hard from this to decipher the atoms and what connects to what. And so we tend to do either make ball and stick models or draw structural formulas like this, because they're a little easier to see the actual connections. And then one other note is we sometimes do a simplified structural formula, sometimes called a line structure, where we make further simplifications because carbon is so ubiquitous. If we look at, for example, here's a carbon atom, there's a carbon atom, we know that carbon always makes 4 bonds, and we know that hydrogen always makes 1 bond, and therefore we can kind of simplify by saying, well, every time there's the end of a line and there's no element listed, like here nitrogen is listed, but there nothing's listed, that's a carbon atom, and we can always figure out if there's any hydrogens that need to be there by counting up the total bonds. So here there's a carbon atom with 1, 2, 3, 4 bonds to it. That's as many bonds as carbon makes, so there's just a carbon there. But here there's a carbon atom with 1, 2, 3 bonds to other shown atoms, which means there's got to be a 4th bond that's not shown to a hydrogen atom out here. And you can see that reflected on the ball and stick model. It's important to note that Not only does every molecular compound have a definite formula, like caffeine has the formula C8H10N4O2, but also molecules of a given compound have a very definite arrangement of atoms. This is a representation of a molecule of caffeine, and it has to have those 8 carbons, 10 hydrogens, 4 nitrogens, and 2 oxygens arranged in exactly this way for it to be caffeine. It's certainly possible to have those numbers of those types of atoms arranged differently, but if so, that is not going to be a molecule of caffeine. It could be a molecule of some other substance. One other thing worth mentioning is that molecular compounds are generally made up of combinations of non-metallic elements. We saw previously that ionic compounds are usually made up of a metal and a nonmetal. Molecular compounds are made up of just nonmetals. And there's lots and lots of examples. H2O, water, is made up of hydrogen and oxygen, both nonmetallic. Octane, C8H18, a component of gasoline, is made of carbon and hydrogen, both nonmetallic. PCl5, or phosphorus pentachloride, made up of phosphorus and chlorine, both nonmetallic. And many, many more. Now, a molecular formula tells you how many atoms there are of each element in a molecule of that compound. N2H4 is the molecular formula of hydrazine. C8H10N4O2 is the molecular formula of caffeine. But we often deal with something called an empirical formula, which is the simplest whole number ratio of the atoms, or it could be ions if we're dealing with an ionic compound, in the compound of interest. We often deal with empirical formulas because in determining the composition of a compound, often that's the original data that we get, or that's what our data leads us to. And for example, if we look at hydrazine, its empirical formula would be NH2, and we get this by noting that the hydrazine, N2H4, these subscripts, the relative number, or the actual numbers of atoms of nitrogen and hydrogen, both of those are divisible by 2, and so we could reduce the 2 to 4 ratio to simpler terms of 1 to 2, and then that's the empirical formula. It's just the simplest whole number ratio we can get for a given compound. So predict what the empirical formula for caffeine would be. And hopefully you would say C4H5N2O, because the 8, 10, 4, and 2, the numbers of atoms of each of the elements for caffeine in its molecule, also can be divided by 2 and get whole numbers, and that's the smallest whole number ratio that we can get. So that's the empirical formula for caffeine. Now, one other thing worth noting is, what would you do if you were given the question, what do molecules with the formula C2H6O look like? Well, you know they're going to have 2 carbon atoms, 6 hydrogen atoms, and an oxygen atom. And if you were told that carbon always makes 4 bonds, hydrogen always makes 1 bond, and oxygen always makes 2 bonds, you would probably end up putting these atoms together and coming up with something like that. However, you might have come up with something like that. Now notice both of those contain 2 carbons, 6 hydrogens, and 1 oxygen. Both of them fulfill the bonding rules for carbon, hydrogen, and oxygen, but they are definitely not the same structures. And these are the ball and stick models of the structure shown on the left is ethanol. It's the stuff that's in beer and wine. The thing on the right is what's called dimethyl ether, and you definitely do not want to interchange these. You don't want any dimethyl ether in your beer, and that would be a very bad thing. So these are examples of what are called isomers, molecules that have the same formula but different structures. There's actually many different types of isomers. These are called structural isomers, just something you should be aware of at this point. And the last thing for this screencast and for our little exploration of molecules and molecular compounds is how do we name molecular compounds? Now, we've already seen things like hydrazine and caffeine that don't have a systematic name, they just have a given name, and those you'll learn some as we go along. But if we're dealing with reasonably simple compounds, what are called binary molecular compounds, they're made up of just two elements, we have some reasonably simple naming rules. We use prefixes to indicate the number of atoms of each element in the molecule, and the first element's name we leave the same, and the second element's name we change its ending to IDE. Now notice this sounds a little bit similar to naming of ionic compounds, but it's different in that we use prefixes. So one thing you're going to have to do when you name is, when you look at a compound, you're going to have to ask yourself first, is it a molecular compound or is it an ionic compound? Because the naming will be different for the two, and you don't want to conflate those. So here's a little bit of practice going back and forth between formula and name. CS2, you would identify as molecular because carbon and sulfur are both non-metallic elements, and then we would use the prefix for one carbon would be mono, but often that's left off. The prefix for two for the sulfur would be di, and we change the sulfur to sulfide. So we could say monocarbon disulfide, but typically we leave off the mono, especially on the first element, and so we would say carbon disulfide. What would a molecule of dinitrogen tetroxide have for a formula? Well, di is 2, tetra means 4, and that means we have 2 nitrogens and 4 oxygens, and remember the oxide came from oxygen. What would you call SF6? And once again, like with the N2O4, we note that SF6 would be molecular because S and F, sulfur and fluorine, are both nonmetals, and this would be sulfur hexafluoride, hexa for 6. How about triselenium pentachloride? And hopefully you came up with Se3Cl5, 3 is tri, penta means 5, and the other prefixes, mono for 1, di for 2, tri for 3, tetra for 4, penta is 5, hexa is 6, hepta is 7, octa is 8, nona is 9, and deca is 10, and that's as far as we'll go for this course. And that's it for the Molecules and Molecular Compounds screencast.